All right, greetings everybody. We are back with another pre-exam recitation. This recitation is going to cover a couple examples that are pertinent to our second exam, which is covering equilibrium, or in our case also chapter 16. And it won't be exhaustive, but it will be a pretty good indicator of the kind of problems you should be getting comfortable with. And we'll just start with this first question. Express the equilibrium constant for the following reaction. 1 equivalent of methane plus 2 equivalents of oxygen gas is in equilibrium with carbon dioxide gas and 2 equivalents of water vapor or water gas. So, to start this out, you'll have to excuse the tablet handwriting here, but remember, for any generic reaction, A equivalents of A plus B equivalents of B is in equilibrium with C of C plus D of D. You can express the equilibrium concentration for that as K of sub C is the concentration of A raised to the A power times the concentration of, wow, I am not starting this off strongly. Products over reactants, folks. Products over reactants. C of C, D of D, or generically products raised to their respective power. A of A, B of B, reactants raised to their respective powers. So in this particular case, if we want to find the equilibrium constant for this given reaction, all we have to do is go to our concentration of our product, so the concentration of carbon dioxide raised to the first power, because that's its constant. Concentration of our water vapor squared, because it's raised to the second power, over our concentrations of our reactants, which in this case is, or are, methane gas, raised to the first power, times concentration of oxygen gas, raised to the second power, because that's our coefficient. So that's the answer in this particular case. Always just look at your products over your reactants raised to their respective power, and you're well on your way to setting up an expression to describe your equilibrium. Next question, scrolling down. Express the equilibrium constant for the following reaction. So for this reaction, we have 4 equivalents of aluminum solid react with 3 equivalents of oxygen gas, and this forms an equilibrium with 2 equivalents of aluminum oxide solid. Now, right out the gate here, because we're asked to express an equilibrium constant for this reaction, you have to be aware that we do not include any solids or liquids in our equilibrium constant because they don't affect the equilibrium constant. So we have to immediately exclude aluminum and aluminum oxide from our expression. And this obviously simplifies things substantially, because now we don't have any product in our expression, and we only have a single reactant in our expression. So for this particular case, because we don't have a product to include in our expression, we just put 1 there as a placeholder, and then in this particular case, it's going to be the oxygen concentration cubed, because that is the number of moles in this balanced reaction. And that's it. Pretty straightforward. But if you attempt to include things you shouldn't, in this case, the aluminum oxide and the aluminum, you're going to get the incorrect answer. So always survey initially whether or not components of your equilibrium reaction are eligible to be included in the equilibrium expression. Moving down. Let's see here. For our next question, the equilibrium constant is given for the following reaction below. Determine the value of the missing equilibrium constant. So in this case, we have two reactions. We have our first reaction on top, hydrogen plus bromine is in equilibrium with two equivalents of hydrogen bromide, or hydrobromic acid. And this has an equilibrium expression, constant of 3.8 times 10 to the fourth. And then we have a second one, where we have two equivalents of hydrobromic acid are in equilibrium with hydrogen gas and bromine. And interestingly, these are opposite reactions, and that's the crux of this particular problem, is the second reaction is just the first reaction written in reverse. And that's all we really need to know to solve this problem, because let's see here, equilibrium constant for a forward reaction is going to equal 1 over the equilibrium constant for the reverse reaction. So all we have to do for this is to say, or vice versa, the equilibrium constant for the reverse reaction is going to be 1 over the equilibrium constant for the forward reaction. So in this case, if we want to know the equilibrium constant for what we'll designate the reverse reaction, because it's second, we can just say Kc for that second reaction is going to be 1 over Kc, and we'll just call this reverse, forward, 1 over 3.8 times 10 to the fourth, and that should give us a small value, let's see, 2.63 times 10 to the negative fifth. So nothing too tricky here. You just need to know how to read a reaction forward and reverse, and how that will affect the equilibria as your reaction is written. Let's see here. Next question. Calculate the value of nitrogen at equilibrium if hydrogen at equilibrium equals 1.5 moles per liter and the concentration of ammonia at equilibrium equals 0.5 moles per liter and the equilibrium constant is 2, given the following reaction. Nitrogen plus 3 equivalents of hydrogen is in equilibrium with 2 equivalents of ammonia gas. So let's go ahead and jump into this one. So for this, let's go ahead and start and just get our expression together, because what we're going to want to solve for is the concentration of nitrogen at equilibrium, but we're given an equilibrium constant. So let's say equilibrium constant for this is going to be our product, so in this case ammonia, squared over the concentration of nitrogen times the concentration of hydrogen cubed. And since we've got this, what we can do is just simply rearrange things so that we're solving for nitrogen, because we have our equilibrium constant, we've got our concentration of ammonia, and we've got our equilibrium concentration of hydrogen. So all we need to do is just rearrange and solve for nitrogen. And we don't even have an exponent in this particular case that we need to worry about. So what I'm going to do is multiply both sides by the concentration of nitrogen, and then divide both sides by the concentration, by the equilibrium constant. And that's going to give us the following expression. Concentration of nitrogen at equilibrium is going to equal concentration of ammonia squared over equilibrium constant times the concentration of hydrogen cubed. Now, all we have to do is substitute and solve. So in this case, concentration of ammonia is going to be 0.5 moles per liter cubed, squared, over equilibrium constant of 2 times 1.5 moles per liter Wait, did I get this? Yes, that's correct. Cubed. And what this will give us is, once we solve it all together, is 0.037 moles per liter for our equilibrium concentration of nitrogen gas. That's not too daunting. Let's go ahead and scroll down and see another one. All right, so consider the following reaction: equilibrium concentrations and equilibrium constant at a particular temperature. Determine the equilibrium concentration of the water gas or water vapor. So in this particular reaction, we have ethane gas plus water gas is in equilibrium forming ethanol, or C2H5OH, all in gas phase. In this case, the reaction is highly favored because the equilibrium is large. The equilibrium constant is 9.0 times 10 to the third, or 9,000. And we have equilibrium concentrations for the ethane, the C2H4, and for the ethanol, the C2H5OH. And what we want is that equilibrium concentration for the water vapor. So let's go ahead and set this one up. Okay. Is going to equal our product concentration at equilibrium, C2H5OH for our ethanol, and that's just to the first power over our ethane. Let me draw that better. Also to the first power times the concentration of water, also to the first power. So pretty straightforward mathematically in this particular case. And all we need to do in this case is rearrange this all for water. So I'm going to multiply both sides by water to eliminate water from the bottom, and then I'll divide both sides by our equilibrium constant, and that's going to give us the following expression. Concentration of water vapor at equilibrium is going to be the concentration of ethanol at equilibrium over the concentration of ethane at equilibrium times our equilibrium constant. So let's go ahead and substitute in here and solve. So I'll just bring it back down here. Concentration of water at equilibrium is going to equal, let's see, for our ethanol, we have an initial concentration, or an equilibrium concentration of 0.015 moles per liter. And then our concentration for our ethane is 1.69 moles per liter. And our equilibrium constant is 9,000, or 9.0 times 10 to the third. And since we could hypothetically be tracking our significant figures in this case, this would have as written two significant figures instead of the 9,000. So let's take a look here. This is really straightforward to solve. In this particular case, we're going to end up with a fairly small value of 9.86 times 10 to the minus 7 moles per liter for our equilibrium concentration of water vapor. And that isn't really too surprising given the fact that we have a really large equilibrium constant that's going to favor, well, I guess technically in the scale of equilibrium constants, this one's not really large, but it's a large equilibrium constant which is going to strongly favor the formation of our product. So it's not out of line to assume that we're going to need a fairly small equilibrium concentration of water in this case, considering that our concentration of ethane is actually larger at equilibrium than our ethanol. So this is actually a pretty nice rational answer. Next, scrolling down. All right. And I think this is the last example categorically. And the exam is going to include, more than just one of these subcategories necessarily. There's going to be a little bit of duplication on the exam. In addition to these, there will be some questions regarding Le Chatelier's principle and how perturbing equilibrium will cause a shift either to the right or the left to account for that shift in equilibrium to accommodate Le Chatelier's principle. So, that said, our last example here, consider the following reaction. Here we have our copper sulfide solid plus oxygen gas is in equilibrium with a copper solid and sulfur dioxide gas. And right out the gate, what should be screaming out to you with this particular example is that we have solids in our expression here, which means the copper sulfide and the copper are not included in our equilibrium expression. They don't factor in. So you really need to make sure you exclude these. Knowing this now, we're going to move through the rest of the question. A reaction mixture initially contains copper sulfide and 2.9 moles per liter oxygen gas. Determine the equilibrium concentration of oxygen gas if the equilibrium constant for the reaction at this given temperature is 1.5. So whenever you're being asked for an equilibrium concentration and given Kc, you're looking at an ice table. So let's go ahead and jump into this. Okay, so let's make a little ice table here. I, C, E, and I like to lay it out just like we would draw our reaction across our x-axis of the ice table, but in this case I'm going to exclude our copper sulfide and our copper because they don't matter. So let's not confound the situation by including something we don't need to. And we'll say oxygen gas and sulfur dioxide gas. Okay, so we've got our reactant that matters and we've got our product that matters. And in this particular case, because we initially only have oxygen in the reaction mixture, because we know the mixture only contained initially copper sulfide and oxygen, the sulfur dioxide is going to be at 0, and we know that the oxygen is given initially as 2.9 moles per liter. Now, change. These are all 1:1:1 ratios. So our oxygen has a 1 and our sulfur has a 1. So our x coefficients, our units of change, are all just x. We don't have to adjust the magnitude of x to account for different coefficients here. So the important thing is we know that they're all just 1x for our units of change, and our units of change, our oxygen is going to decrease because it's being consumed, and it starts with the highest amount possible initially. So it's going to lose 1x of concentration before hitting equilibrium. And the sulfur dioxide, because it started at 0, has to go up. It's going to go up plus x. So fairly straightforward example here. So at equilibrium, we can express our equilibrium concentration of oxygen as 2.9 minus x moles per liter, and we can express our sulfur dioxide as just x. And now that we have this, let's take a look at our equilibrium expression. So our equilibrium expression is our equilibrium concentration. In this particular case, is going to be the concentration of our product that counts, sulfur dioxide, raised to its coefficient, which is 1, over the concentration of our oxygen at equilibrium, raised to the first power also, because that's its coefficient. And now that we have this, we can just substitute in our equilibrium concentrations from our ice table, and we see that the concentration for sulfur dioxide is expressed as X. The concentration for O2, or oxygen gas, is 2.9 minus X, and this is going to be set to equal the equilibrium concentration of 1.5, which was given in the problem. So now it's just a little bit of arithmetic, right? So let's see here. Probably the easiest way to go about this is to multiply both sides by 2.9 minus X to get it off the bottom of this fraction. And if we do that, we can say that X is equal to 1.5 times 2.9 minus X, and then we'll just distribute the 1.5, and that'll be 4.35 minus 1.5 X equals X, and then we can just add 1.5 X to both sides, so that'll give us 2.5 X equals 4.35, and then we divide both sides by 2.5 to get rid of it, isolate X, and that's going to give us 1.74. So this is really close to the answer, but this is not the answer we are seeking, because this is only the value of X. And the question was, determine the equilibrium concentration of oxygen gas. And the equilibrium concentration for oxygen gas is not X, it's 2.9 minus X. If you were to report the answer as 1.74 moles per liter, you would be accidentally indicating the concentration of sulfur dioxide as your answer. So to get the concentration of oxygen is going to equal 2.9 minus X moles per liter, so this is going to be 2.9 minus 1.74, and just for ease of calculation, we'll say it's 2.9 minus 1.7, and this is going to give us 1.2 moles per liter. So that would be the correct answer for this particular problem. I think this is a good way to get you guys started for the exam. Use this as a guide for the kind of problems you should be solving, as well as doing a little bit of extra problem solving around Le Chatelier's principle and some of the general other principles that we discussed in lecture. But I think this is a pretty good start. So good luck on the exam over the next couple days, and I'll be catching up with all of you later.